they can see my screen. So it is mathematical research. So let's start with a little survey, in particular you guys. What is mathematical research? Let's just see if we can just end this right now and go home after a 5-minute seminar. What do you think when you hear mathematical research? What do you think it means?
You're working on a problem or a topic.
Okay, so you're working on a problem or a topic. Okay, let's try to kind of dive a little deeper.
You're doing some reading.
Okay, so you get some reading, get some background.
Maybe doing some modeling.
Okay, maybe come up with some modeling. Okay, great. Anything else?
Writing about what you're doing.
Okay, so you're right about what you do. You got to share your ideas. Okay, so I'll try to address the topic of what I think research is in the introduction here. Then I've got the process of research, writing a deductive proof, final stages, return to stage one because we go back to the beginning, and then I'll talk about an example of a research program. Okay, so let's start with a couple of attempts here. So some people might say this: doing research means proving theorems. That's what a mathematician does. A mathematician proves theorems. Paul Erdős said that a mathematician is a machine that turns coffee into theorems. Okay? And I would say, yes, this is true, but it's only part of the picture. Like, for example, in advanced calculus, every class we prove at least one theorem. Every class I assign at least one theorem to prove for homework. On the exam, you had to prove 2 theorems, right? You had to do that. Limit of a sum is sum of the limits. And what other one did I give you? I think I gave you another one. Oh, no, okay. It was actually a specific, sequence that I wanted you to find the limit using the epsilon big N definition. But there were a couple theorems on the take-home portion too. One of them was about those Cesaro means. Okay, so they had all kinds of theorems. Now, this is a question for you guys over here. Would you consider doing an advanced calc class research? I probably wouldn't consider that research. Okay, so it's got to be something other than proving theorems, because if research was proving theorems, then that class would be research, because that's all we do. Okay, so there must be something else to it. All right, so let's try another thing. Okay, maybe this is what research means. If you look maybe at some faculty member's webpage, you go, oh, that guy does a lot of research. Look at all the publications he has. So maybe research means publishing papers in mathematical journals. And I think, yes, that's also part of it. But I still think there's more to it. For example, if I submit a paper and they say, no, we're not going to take that paper, does that mean I didn't do research? I mean, I think I still did. I just didn't get the paper through. So there must be more to it than getting the paper in there. Because I think this confuses the product of research, which is that paper, with the process of research. And that's what I want to talk about right here, the process of mathematical research. Because for other sciences, I think the general population at least has a conception of what it means to do research in chemistry. Right now, it may be a very flawed conception because they may picture a guy in a lab coating test tubes and things bubbling and beakers and whatnot. Okay, but a chemist does experiments in the lab, tries to draw conclusions from those experiments. Okay, that's chemistry research. A biologist might collect samples or might, do experiments in a lab with petri dishes and worms and injections and whatnot, and try to draw conclusions from those experiments. But if I were to ask a generic person on the street, what is mathematical research, I'm not sure they would have a baseline conception of what that was. In fact, I've had somebody say, well, isn't math kind of solved? So, but I mean, there's a lot of results. Math is an old field. Don't we actually know how that works already? Why do we need to research mathematics. So I want to get into this process of mathematical research. Oh, you know why I didn't start at the beginning? You notice I didn't have a title slide? Let me show you what I did. I started with an old Beamer presentation and changed except the title page. I forgot to change that. So it's supposed to say, what is mathematical research? I'll go back and change it later. That's what I would just point that out. Okay, so let's get into this thing, the process of mathematical research. Okay, now, I apologize in advance for this slide. I don't like slides with a lot of text on it, but hey, I had to do it. All right, so I'm gonna go over these 6 kind of broad stages, okay? And I think they're all part of it. Now that publishing papers, that's way down here. That's part of communicating your findings, and that's only one way to communicate your findings, publishing the paper, okay? There's other ways to do it, like what I'm doing right now is a way to communicate research findings. Okay, so it starts with observing a relationship between quantities or structures. In mathematics, we don't have labs, but I still maintain that we do experiments. Seek to explain why the relationship holds. So you experiment to see if you varying certain quantities keeps the relationship holding. Try to explain why it holds. Once you can do that, then try to write a deductive proof. If you can get that, see if your result generalizes, and then work on communicating your findings. Okay, so I want to do an example of a little research thing. Okay, 1, 2, 3 people should already know this. So I will let you do it from here. Okay, Tanner, what's this?
That's a triangle.
That is a triangle, right? So we've got a triangle, sides A, B, C. Okay, I've got the side lengths listed for us right there. And I've got a semicircle constructed on each of the legs, okay? And one on the hypotenuse, okay? So I want you to notice something. That plus that and that, okay? So 4.54, 13.59. Okay, so 4 plus 13 is 17. The 0.5s will bump us up. Now we got 18. 0.4 plus 0.04 plus 0.09 is 0.13. 18.13, I don't know if you can see that out there. It's green on green, okay? But it seems like there might be a relationship, okay? So we've got the areas given. It looks like this area plus this area equals the green area, okay? Now, if you go on just one example, you're not doing math, okay? If you try to prove a theorem based on one example, you're doing math wrong, okay? There's no wrong way to do it, but you're doing it wrong. Okay, so what we might do is we might try varying these lengths. We might experiment. Does this relationship still hold if we change those things? So I got a little app going here. Triangles. Okay, so this is my little GeoGebra app here.
And yes,
Okay, so
you
here's
can
my
see
question. If I change the lengths, let's see what happens. Okay, so I did some changes there. Drag that, made this longer. Okay, so now I got 4.54, 22.73, 26. What is that? 27.2, 27.27. Okay, looks like it still holds. Let's mess with it a little bit more. Change that. Oh, the whole thing changed. Change that down. Change that out that way. Okay, what do I got? 1.15, 14.43, 15.58. Okay, so it looks like no matter what I do with this triangle, the relationship is holding. Okay, so that would complete what I would call the first, the second stage. The first stage was notice a relationship. The second stage, experiment with examples. Does that relationship still hold when you change some of the variables? Okay. So now, on to the third stage. Why? Why does it work? What is happening? Okay, so we're trying to make sense of what we're seeing in light of what we already know. Okay, so what do we know about triangles? I know exactly two things.
Their interior angles equal 180.
Oh, I know three things. What else do I know?
1/2 base times.
Okay, one half, I know how to find the area. You give me a triangle, I know how to find the area. You give me a right triangle, and I know the side lengths satisfy the Pythagorean theorem. Okay? So that's something I know about triangles. We had right triangles in here, so maybe this is important. I don't know. And of course, I also know how to find the area of a circle, right? I only know how to find the area of actually two shapes. I know how to find the area of a circle. I know how to find the area of a rectangle. You say, hey, don't you know how to find the area of a triangle? Yeah, but every triangle is half a rectangle. Okay? So a circle is one of the two shapes I know how to find the area of. If the diameter was A, and I want to find the area of that circle, well, my diameter is A. I got to cut that in half to find the radius, A over 2, and that's why this is there. You take the radius, you square it, you multiply by pi. Why is this here? Right, because on those legs, I did not have circles, I had semicircles. You might say, hey, Dr. McNamara, you said you knew how to find the area of rectangles and circles. What's with this semicircle business? Well, of course, you just cut the area in half. Okay, so I got that. All right, so I know those two things. All right, so the observation that we made before mathematically can be said this way. This is the area of a semicircle on that side length A. This is the area of a semicircle on side B. This is the area of a semicircle on the hypotenuse. And what we were saying was this plus this equals this. Okay, do some arithmetic and you get this. Where are the 8's coming from? Right, you square in this, so a over 2 squared means a over 2 times a over 2, a squared over 4. You got the other factor of 1/2 there, so you get an 8 downstairs. And the pi is just going to come along for the ride. Okay, so you got common factors there. Well, divide both sides by pi, multiply both sides by 8, and you get this. Okay, so it seems like that relationship between the circles is holding because the Pythagorean theorem is holding. Okay, the relationship that we saw between the semicircles comes down to the fact that the Pythagorean theorem gives us a relationship between the side lengths. Okay, so we're understanding why it works. Now the next stage would be trying to write a deductive proof. You might say, well, didn't you just prove it? Doesn't this prove it? Brock, why doesn't that prove it?
One example.
No, I've got general values. I've got A, B, and C.
Think of section 1.4 of your calculus book.
Yeah, he did Larson. Tanner, why doesn't this prove the theorem?
Is that your scratch work? Can you start with something you know?
Okay, right. You've got to start with a previously proven theorem. You cannot start with this. That's my conclusion. Okay, that's not what I know already. So I can start with definitions. I can start with previously proven conclusions, whatever, right? So we started with this. We can't start there. We got to end there. Okay, but it's not hard to get from what we did to a deductive proof. Okay, so we have this little theorem. We have a right triangle. We construct semicircles on each side. The area of the semicircles on the hypotenuse, or the area of the semicircle on the hypotenuse is equal to the sum of the area of the two semicircles on the legs. Okay, so here's what we would start with the Pythagorean theorem. We treat that as known. If you want, you cite it in Euclid's Elements and tell them where to find it. I forget. Book 1, something or other. Okay, and then we just redo our calculations basically backwards. Okay, you guys in advanced calculus, when we do our scratch work for finding big N, your proof is basically just writing your scratch work backwards. You find an expression that gives big N in terms of epsilon, and then you go backwards and work it out and got your proof. Okay. So, that kind of gets us to what I'll call the final stages. Try to generalize. Okay. Let's go to that other GeoGebra app. Whoop. Okay, where is it? Here? Okay, there it is. Clearly. All right, here, I've got a right triangle. And on that right triangle, I have equilateral triangles. Okay, on each leg of my right triangle, I constructed an equilateral triangle, or I had GeoGebra construct an equilateral triangle. Let's look at the areas, right? There's the hypotenuse right there. 33.9. Let's look at these guys. 24.98. 8.92. 24 and 8 is 32. 0.9 plus 0.9 is 1.8. So now we got 32.8. 0.08 plus 0.02 is 0.1. Gets us to that. Looks like it holds here. Okay. So a couple of things to do. I could play with the side lengths a little more, make sure it's still going. What else could I do?
Change the shape.
Right, you guys know what this is, right? What's this thing?
Slider.
Slider. What's it do?
Changes the number of.
Right, so I got a slider for my variable n here. By moving this, I can change the value of n. Okay, n equals 4. Now we got squares. This is the Pythagorean theorem, right? The square on side A plus the square on side B equals the square on side C. Let's see if it works for pentagons. Let me zoom out a little bit. Okay, so I got regular pentagons constructed on the two legs and the hypotenuse. We can check, add that and that. Does it total out to be that? Okay, it does. So it actually looks like we can generalize the Pythagorean theorem not just to squares, but to any regular polygon constructed on the side length, and also to semicircles, which is the case that we looked at just a second ago. Okay, so how would we start working on this? Well, we might try to come up with expressions for the area of these polygons in terms of the side length. I bet that the expressions we come up with have something that is proportional to this thing squared. I bet the area of this thing is proportional to 4.45 squared, somewhere in there. In fact, in tech and programming, we did it, and of course, you remember what it was? What was it? Okay, well, it's not too hard. The strategy we used was we cut these up into isosceles triangles. We cut them up into 5 congruent isosceles triangles. We use something about the angle, okay? And the vertex angle here is determined by the number of sides, okay? And then we use a little trigonometry to get the height, and then we got the base, and then, so it actually does work out. So it is a neat little project to generalize what we found. Okay, so we had observe and observation. Experiment. Make sure your observation holds in context other than the first one that you saw. Try to think about why it works. Okay, think about what you already know and try to relate that to what you're seeing. Okay, then once you've got that, do your deductive proof. So those 2 stages are, in fact, the first 3 stages are kind of hidden sometimes. Like I mentioned, some people say math research is proving theorems. Okay, well, how do you do that? Well, you observe, you experiment, you try to figure out why it's true. If you can't come up with examples of your theorem, you shouldn't try to prove your theorem. Never try to prove a theorem unless you are convinced the theorem is true by looking at examples. And sometimes looking at those examples very carefully can show you the steps you should be thinking about to use in your proof of your theorem. Okay, so let me switch back here to my slides. Okay. And then the sixth stage is communicate your findings. Okay, so now that you've made your observation, you've experimented a little to see if it actually works, you try to understand why it works, you write up your deductive proof, you try to generalize it as much as you can. Now you think about doing that last stage, which is communicating your findings. So you submit your work to a conference, or you write it up and submit it for publication in a journal. Now, the standards for you guys, so this side of the room versus this side of the room, there would be different standards, okay? If I submitted that work, well, they would probably laugh at it. And they'd say, you're a professional mathematician, right? This is already well known, they might say to me, okay? Now, honestly, I don't think it's all that well known, because I've talked to people that didn't know it yet, okay? But the standards for a professional mathematician would involve some originality, okay? Some making sure you're not duplicating any old work or anything like that. The standards for undergraduate research, a little bit different, although depending on how you did it, depending on how I did it, I might be able to publish something in an expository journal where we kind of explain results a little bit more. But anyway, all that stuff is the product of research, the last step in this process of research. Okay, so a couple of other things I wanted to talk about. Let's go back to stage one, because I kind of swept something under the rug there. I just gave you a triangle and said, here, look at this triangle and these circles. And then we said, okay, well, does it seems like there's a relationship between the sum of the areas on the legs and the area on the hypotenuse. So we try to understand what's going on there. But like, if somebody doesn't say, here, look at this thing, like, what do you do? So a big part of research is forming conjectures, okay? Let me see, somebody related a story, I forget who it is. A relatively famous mathematician, Julia Robinson, was she was part of the University of California system, and sometime in the 70s, they said, okay, well, we gotta see what the faculty are doing. So you gotta tell us what you're doing every day. And she said, Monday, tried to prove theorem. Tuesday, tried to prove theorem. Wednesday, tried to prove theorem. Thursday, tried to prove theorem. Friday, theorem false. Okay, now I get it. She was probably being a little facetious that she didn't want to have to report what she was doing every single day. And this kind of is going to sound like semantics, but to say theorem false, what's the problem?
It wouldn't be a theorem.
Not a theorem, okay?
Conjecture false.
She tried to prove a conjecture Monday, Tuesday, Wednesday, and Thursday. And then on Friday, she must have produced a counterexample to show that the conjecture was false. So,
But that's already valuable.
yeah, that is valuable.
quite valuable.
That's valuable research as well. Okay, so for you students, the difference between a theorem and a conjecture. A theorem, they're both statements, okay? They're both statements. A theorem is a statement where we have a deductive proof that that statement is true. A conjecture is a statement where we really don't know yet. Okay, now, I don't mean nobody knows yet. Okay, because some of these things are in obscure places, or they're in parts of mathematics that aren't really part of the standard curriculum anymore. Okay, so when I'm talking about making a conjecture, I'm making a statement that I think might be true, but I don't really know yet. Okay, so the process of mathematical research begins with forming these conjectures. All right, so let's talk about how we might do that. Okay, so you might have heard of this topic. Okay, comes up every once in a while as a fun mathematical fact. The idea of a perfect number. So a number is quote unquote perfect if it is equal to the sum of its proper divisors, the divisors that are strictly smaller than the number, okay? So of course 6 divides itself, but that's not a proper divisor. Okay, so 6 is 1 plus 2 plus 3, 28 is 1 plus 2 plus 4 plus 7 plus 14, I hope. Is that 15, 17, 21, 20, okay, great. Okay, so those are 2 examples of perfect numbers. All right, so couple things. We notice both of the perfect numbers that we see are even. So we might form a conjecture. Perfect numbers are even. Okay, now we only saw 2 examples of perfect numbers. How can we create more examples of perfect numbers? Tech and programming people. Right. Write a Python program to find perfect numbers. Okay, you could have your program run overnight. Test the first 10 million integers. Figure out which ones are perfect by putting a little loop in there and having the program add up the proper divisors and see if it totals out to the number you're testing. If it is, you got a perfect number. Okay? So you can experiment, see if you can generate more perfect numbers. Are they still even? If they are, then that adds a little bit of weight to think, okay, maybe our conjecture is true. Remember, don't try to prove something unless you're convinced it's true. Okay, so we could start working on a proof about that. If we can't prove that, well, we might try something else. Maybe we could look at the numbers in a little different manner. Maybe it's something different than them just being even. That's important. If we notice this, okay, 6 of course factors into 2 times 3. That's kind of so simple that it hides the pattern. Here's another perfect number. We saw that one, right? 2 squared times 7. 496 is the next perfect number. When you write your Python program, it'll come up. Okay, this one also factors into 2 power 4 times 31. So we might see, okay, maybe instead of our even conjecture, if we can't prove that or if we can't figure out why that's true, maybe we try this. Maybe we say, okay, let's assume we have an even perfect number. Can we prove it's of this form? Okay, 2 to this power, 2 to some power, and then something over here. One thing to notice about the somethings over here, 3, 7, 31. This is 1 less than 2 to the 5th. This is 1 less than 2 to the 3. This is 1 less than 2 to the 2. Okay, and notice that's 1 less than 5, right? This involves 2 to the 5th, 2 to the 5 minus 1. 2 to the 3rd is involved here, 3 minus 1. 2 to the 2, 2 minus 1 is your exponent there. So maybe we can prove something that says if we have an even perfect number, then we got something of this form. And that's if we couldn't prove this. Dr. Rivera?
Yeah, the state-of-the-art knowledge is that that hasn't been proved.
Right, so I don't think it has been proven yet. Okay, so you might come up against a conjecture and like, okay, I can't quite get that. Can I get anything else? Is there a different way to look at what I'm seeing and try to make some progress there? Okay? And I guess a counterexample would be also pretty good there, because that would show that the conjecture about every even number being, every perfect number being even is false. If you could come up with a counterexample, that's also, like Dr. Doherty said, that's also valuable progress. Okay, now these were all kind of like isolated things, right? We had the triangle with the circles. And we were able to generalize that a little bit. We had a triangle with not circles, but regular polygons constructed on the legs, and we saw the relationship between the areas. Here we got perfect numbers. Okay, kind of an isolated one result thing. But there are some things that you might encounter, a research program. Okay, some of these can be pretty sweeping and substantial, a research program. So here's what I want to talk to you about. Okay, who's taken modern algebra? Tanner, Brock, Taryn, you'll have taken modern algebra. You remember doing this? You sometimes get to this at the end. You gotta have the conception of an isomorphism. Okay, two groups being structurally the same. Okay, the groups might show up as something different than what you normally do. Like this could show up as integers mod 4, or it could also show up as complex numbers modulo, or complex numbers of unit length, roots of unity, in other words, 1i, -1 and -i. That forms a group that has the same structure as the integers mod 4. Okay, so you might start to do this for groups of small order, at least. Okay, so if you're talking about a group of order 2, well, there's only one. It's got to look like that. It gets a little more interesting as you get down here, because now you have a couple different options. If you have a group of order 6, it either looks like this, which is isomorphic to Z6, or it looks like this, S3. Okay, and I forget how far our book goes in doing this, but I remember doing this the last time I taught modern algebra. Okay, so sorry, a lot of text, but if this is a fairly substantial result, and it took quite a while to prove this research program. So there is something called the classification of finite simple groups. Okay, the reason I was writing it like this, Z2 cross Z3, rather than saying Z6, is, well, Z6 has these two guys as subgroups, normal subgroups. So in a way, these guys are more fundamental than Z6. Okay, so the classification theorem of finite simple group says every finite simple group is either a cyclic group, like Z6 or Z3 or whatever like that, alternating group, okay, those are even permutations. Do you remember your permutation notation from your modern algebra class? You start out by writing two rows of numbers. The top is like 1, 2, 3, 4, 5, and the bottom has those numbers, but sometimes they're shuffled. And then you remember kind of breaking them up into this little cycle notation. You kind of write it like 1 goes to 3, 3 goes to 5. So you would write like, oh gosh, 1 goes to 3, 3 goes to 5. So you would write 1, 5, 1, 3 or something like that. I forget how it goes. I have to relearn it every time I do it. Okay, but those are your alternating groups. There's an infinite class called groups of Lie type, and then there are these handful of exceptions, 27 quote unquote exceptional groups. Okay, so the proof of this classification isn't something you would find in the textbook. Okay, now you might do a survey course in graduate school about this. They can probably get it down to the essentials there. But the proof does consist of thousands and thousands of pages. There was almost 100 people that worked on it over the course of almost 50 years. Okay, so that's probably the biggest example I know of a research program where you got bunches of people working independently, sometimes proving very small results, but that gets you that much further to getting the whole classification. You know, for example, maybe in the 1950s, people were getting PhD theses, getting doctoral degrees awarded to them for classifying all groups of order 100 or something like that. Okay? So, kind of a bigger example of an overarching program. So the punchline of all this, the thing I wanted to emphasize, is that you don't need a ton of mathematical background to start in on mathematical research. What you need are conjectures, okay? So find a faculty member you like to work with. Try to come up with some conjectures that we might be able to attack, that we might be able to make progress on figuring out whether or not it's true, okay? Try to stay away from the big famous problems, okay? There are lists of unproven problems, right? The Millennium problems, the Hilbert problems from 100 years ago, okay? And I mean, you know, don't be afraid of those, but don't try to make progress on those. Start with other things. Start with smaller things, okay? Work on those conjectures and kind of build up your research muscles that way. And some venues for, certainly for you guys, would be Kappa Mu Epsilon has a convention every year, a regional convention. Kappa Mu Epsilon is a National Honor Society. We have a chapter of here. So I think Brock is in. Tanner, are you KME yet? Okay, we'll have to get you in KME. Karen is in KME. Emma, I don't think you're in yet, are you? Okay, so we'll need to have an induction ceremony. You have to have passed Calculus 1, you have to have a sufficient GPA, so there is something to do. But that does give you a venue for doing research. Okay, if you get a chance, Karen, not last year, the year before, we went over to, oh gosh, I believe it was in Tahlequah. We went to the MAA sectional meeting, okay? That gives you a venue. Plenty of undergraduate students presented work there, research that they have worked on, okay? There are journals devoted to giving undergraduates the opportunity to publish their work, okay? But the whole thing is you just got to get started on something, okay? So don't be too intimidated by the concept of mathematical research. It means coming up with a conjecture, doing some experimenting, trying to understand why it's true. If you can do that, you're probably close to getting a deductive proof. Try and generalize it as much as you can, and then communicate what you found. Okay, I think that's my last one. Yeah, this is either the battery's dead or that's my last one, because this is time over. Okay, no, that's my last one. Okay, so any questions?
Yeah, you said in advanced topology was one of the big branches of math. What are all the what are the main branches of math?
Okay.
Not all, I guess.
3. Okay, no, I guess broadly speaking, analysis is one of them, right? So analysis is the branch of math, I would say it's the branch of math that deals with infinite processes. So anything that involves limits, or taking a supremum, or an infimum, or anything like that, interchanging those processes. So derivatives, integrals are, of course, defined in terms of limits. So calculus is part of analysis. So analysis, one big thing. Algebra, one big thing. Now they aren't totally separate, okay? Dr. Ghosh, what would you say your research area is?
I would say analysis.
Okay, so what kind of analysis?
Well, there are different kinds. You can do advanced calc, and then you can do, like, you are taking a complex variable class. So it's called complex analysis. So if you do like kind of advanced calc on complex numbers, so you do all kinds of things like that. So you get complex analysis, and then also what you guys are doing in linear algebra, that leads towards another field which is called functional
analysis, right?
Kind of a generalization of that field.
Yeah, so I would almost say functional analysis uses techniques from algebra and topology to answer questions about analysis. So yeah, topology is, and there are branches of topology, right? The topology we started today is usually called point set topology. There's algebraic topology, there's geometric topology. And all those try to answer various questions. There's a subfield called knot theory, K-N-O-T, a subfield of topology that deals with simple closed curves and tries to figure out, okay, how can we look at a picture of two different knots, let's say, how do we decide whether they are the same knot? Is there some condition that we can put on the pictures to say, okay, this knot is just this knot? Because remember, you're dealing with a simple closed curve in 3 space, right? So somebody looks at me and they might say, okay, Dr. Mack has brown hair, kind of a gray mask, pink shirt, gray pants. Well, if somebody were looking at me from the top, they'd just see the top of my head and they just see my shoulders, okay? How could somebody looking at those 2 pictures say, okay, this is the same object, but we're looking at it from 2 different perspectives? Okay, and that's what kind of knot theory is about, and those are branches of topology. What the hell did I talk about? Algebra, analysis, topology. I guess those would be the 3 main ones, because those are the ones like if you were to go to graduate school, you would probably take 3 courses, and that would be kind of the big 3. Take a course in algebra, analysis, and topology. That's by no means the whole thing. You got discrete mathematics, that stuff we talked about with graph theory, or was it just Emma? Oh God, it was just Madison, who isn't even here. Okay, well, we did something about graph coloring, where we had these vertices and connections and things like that. So, discrete mathematics would contain graph theory. The number theory that we're working on with Perrin, you could say that's part of algebra, but the way we're doing it, it involves more counting and stuff, like combinatorial number theory. So you could very well say the number theory that we're talking about is part of discrete math. So that's view from 10,000 feet.
Well, the function, so the field I work on is the kind of combination of complex analysis and functional analysis. And the topic is called uniform algebra. So you can kind of guess, like it's a kind of algebra thing. So things get mixed up there. Like,
Yeah, they're definitely not distinct areas. And it's almost like the more kind of crossover you have, the more interesting it becomes in a way.
I guess another field would be differential equations when you go and then PDE and ODE. I think that's another field we can.
Yeah,
Kind of applications.
I did PDE, in particular variational calculus PDE, and it would not work if not for functional analysis. Functional analysis, you deal with these linear spaces that have topologies on them, and you have to be able to prove that a solution even exists. Even if you can't find it, you have to at least be able to prove it exists, and the space has to have the right properties that it can exist. So you can't get away from, usually subless spaces is what we use, but you can't get away from functional analysis in order to make that work. The way I usually phrase it, I tell people, if you want someone to get your spaceship to Mars, you need an analyst, but if you want someone to beat your friend at chess, you need an algebraist. You know, those are kind of the mindset. Somebody who's good at chess is usually a good algebraist. Somebody is good at, figuring out, what you would have to do to a rocket to get it where you want it, given all the gravitational fields and all that stuff. That's more of a calculus problem, more of an analysis thing.
But now what if you want to use the rocket to play chess when you get to Mars?
Just put a missile on it and take out the whole chess screw. That's what I hate chess. I'm a lousy chess player, which is why I want to do analysis.
Okay. All right.
By the way, the knot theory you mentioned, I heard last year that there's one from one student who was working in, I think in biology. They said they need something from the knot theory.
Huh.
So I was wondering, like, it's not always you think, oh, this is just for fun. It's not just for fun. There is a practical applications of things. So, knot theory is one of them. And
Yeah, so, right, like Dr. Go said, some of these things have applications that you wouldn't think they have. Just like the stuff we were talking about in math club when it was just me and Madison and we were doing graph coloring. That has applications to scheduling. I think Perrin, when Perrin was in math club a year or two ago, we did a thing on, were you there? Were you there when we did the graph coloring? I don't think so, maybe not.
I don't think so.
Oh, okay, but you probably remember the graph coloring one. We had a bunch of scheduling problems of, okay, we have this many groups and there's conflicts here, here, and here. How many time slots do we need to accommodate all the groups, but use the minimum number of time slots? So you wouldn't think something as silly as, okay, color this one blue, color this one red, color this one green would be able to solve that problem, but it does. Okay, so if you are interested, all I did was Google math millennium problems or math millennium prize problems. These are from the Clay Mathematics Institute. I think some of these are already done, right?
I think.
Yeah, the pointer conjecture, that's
Point
it.
conjecture, it is proved. Riemann hypothesis still open, I wrote about one. I don't know about the status of this one, P versus NP. I have no idea what that even is.
Just I want to mention about the Navier-Stokes equations, that is not solved, but it is partially solved. And you know where this is method application? The Disney movies you see, all the like water falling or snow is, those are not real. Those are all done through those equations. I mean, at least some.
You just ruined my childhood, sorry. Ah.
Sorry, I just saw it, Tom, on that
Elsa
one.
is not real.
Not gonna even bring up Santa Claus. On that crossover thing, I wish Dr. Chang were here to mention it, but I remember when she was finishing up her thesis or working on it. Another aspect of this is you want to look to see what other people have done, because you don't want to have to reinvent every wheel. So she was working on this thing. It had to do with optimization on nonlinear manifolds. So it's not that hard to explain, but there was a part of it where she thought, maybe, I think you can do this. She's not sure, but she didn't want to, if it had already been done, she didn't want to reinvent it. So we were at Purdue, and Purdue had a big several complex variables group. We were talking about programs. They had a big group of people in that field working there. And she went into this fellow's office, and he probably had seen her around the math department. And she started asking these questions. And he was happy to meet with her. He went through the whole thing. And at the very end, he had showed her that, yes, you can do this and whatever. And she said, okay, thanks. And in the end, he said, so, whose student are you? And she said, well, I'm actually in industrial engineering. And he was so happy. He said, my God, this is actually useful in the real world. She's like, yeah, this is where we're using it. He was so happy. He was a fairly, Carl Cohen, I think was his name. I'm not sure. I think that was the guy.
Yeah.
I think that was the fellow at Purdue. He was fairly famous in his field. So yeah. Where you get the inspiration for the problem you want to study, you don't know. I mean, if you have a university that has all the math journals, and there are 200 good journals or something, you're looking through that stuff, and sometimes you'll see something and think, wow, I didn't know that. And you take something of your own thinking, you apply it to that and see if you can do something else. And sometimes it's a matter of, like my advisor gave a talk once, and he wanted to prove this theorem, and he said, okay, here are all these hypotheses that seemed very nice, and then he had this one last hypothesis that just seemed really specific. And they said, why are you putting that one in there? He said, so that I can actually prove something. Sometimes you can't prove the big picture, but if you throw enough other conditions on it, you can get something out of it. And then maybe someone else can come along, relax the problem a little bit and generalize it and, work from there. So sometimes you end up proving really specific theorems, but in the general picture, you're picking away and getting more intuition into the big picture. So it was a great talk, but it's like, yeah, where'd that one come from? Well, he got a certain distance in a proof, tried to, realized he had a gap, threw another sort of ad hoc hypothesis into the thing, and that made the whole thing work. I think any of us could probably give a whole another 2-hour talk about research and how it, the different ways that people come upon inspiration or prove things, or the social aspect of it, or You know, I mean, when you say you give people a question and tell them to answer, that's not really research. Somebody might quibble with that because for that person, it is research, except you know what the answer is, right?
That's true,
You
yeah.
know, unless you make it open-ended, is this true or false? And then for them, they're doing research. So, and I think that we allow undergraduates to call it research, even if it's somebody
Right,
in
so,
Pakistan has already solved the problem. You
Yeah.
know?
totally, yeah. I mean, even if it's something that's already known, but you come at it from a different angle or a new way of looking at it, that's also valuable, even if the result is, like I said, well known.
There is a, I think, is it in MA journal that you have like the series you have in talk to, like they prove things pictorial, so you just, without any words, so.
Okay,
You
yeah,
can do
picture
it.
proofs, yeah, that's,
proves
I
it.
think that's something that comes up in the monthly.
Yeah, I
Occasionally,
think
they'll have
I'm
a picture proof. And there are actually books in the library where they've collected those, and it's just picture proofs. And of course, the idea is to try to understand why the picture gives you the proof of the result. Okay, so any other questions or comments? Okay, so go out and start forming conjectures.
That's it.
Okay,
Thank
you.
We'll go ahead and stop the recording here, and we'll, no, I will stop the recording here. This is where the recording is happening. So we'll stop screen share.